data or not. So take a look at it. Yeah, as you can see, there's a lot of text in here, so you want to kind of get your way through it. Get started on it. Don't wait till 2 weeks from now. Kind of, especially on the math part, you can kind of get most of this done this week, so you have plenty of time to do the kind of actual data analysis here. Okay. Right. That's everything I was going to show here, just to show the homework. Okay, so today what we're going to talk about is how to make, or start to talk about how to make what are called non-informative priors distributions in Bayesian analysis. So what we saw last time was conjugate priors, and really the time before that also we were still doing the conjugate priors with Bernoulli. And so, for instance, with the beta distribution for the Bernoulli parameter, we saw that you can, depending on how you choose that beta distribution, you can actually affect the posterior distribution, right? And so in the code example from the class from last week, we saw that the beta distribution would, that the posterior is basically a compromise between the prior and the likelihood. And depending on how strong you make the prior, and also depending on how many samples, how big your sample size is in the likelihood, it might be much more tilted towards the likelihood or much more heavily influenced by the prior, depending on the relative strength of the two. And the same thing with the Gaussian, we saw with the conjugate priors for the mean that when we derived the posterior distribution, which was also Gaussian, remember the mean, posterior mean was a compromise, a weighted average of the prior mean and the mean of the data, remember? And so the point is, in all of that analysis, anytime you use these types of priors, you are injecting some type of information into your analysis. You're injecting some kind of prior information. And as you're going to see in the homework, this sometimes makes a lot of sense. So in the homework, what you do in the Alzheimer's disease hippocampus study of that data, what you're going to do is you're going to take information from a previous study on a different data set and use that as prior information for your analysis. Okay. I don't want to give away the punchline there, but you should check the questions about thinking about whether it was a good idea to do that, and so forth and so on. And obviously, this is as we always say in class, always check the assumptions you're making and check your models at the end and try to verify that they make sense. And so you'll get a kind of experience doing that. But it's very often the case, and probably more often than not, it's the case actually, that we don't have a previous idea of what we think the parameters are going to come out to look like. Okay? And we want to be as kind of non-committal as possible about what information we inject into our analysis through the prior. Okay, and so that's what we're talking about next, is how to come up with priors that are as non-informative as possible. Now the problem with that statement, non-informative as possible, is that there's no agreed upon definition about what does it mean to be non-informative. Okay, so this is why, again, the homework, when you derive some of this or think about some of this for the Poisson distribution, I'm going to ask you to give two different non-informative priors for Poisson because there's not a single definition of what it means to be non-informative. So today what we're going to be talking about is what are called maximum entropy priors, and this is what was discussed in the Janes article. I'm going to be talking a little more broadly than what the Jane's article, or I'll give some examples that were not in the Jane's article, I should say. And then on Tuesday, we're going to talk about what's called Jeffrey's prior, which is a different way of describing non-informative prior, and it actually leads to sometimes different priors in the end. But they're both at least some variation on the theme of being non-informative. Okay, so that's our goal. Let's see. Okay, so today we're talking maximum entropy. So let me get to do a quick survey, just I always like to know what everyone's getting into here before I get started. So how many people are familiar with, has come up in a class you've studied the concept of entropy of a probability distribution? Okay, so oh wow, so just maybe a couple people. Okay, that's cool. Good. That means you'll learn something in this lecture then, if nothing else. If no one's ever heard of entropy, then maximum entropy is certainly a new concept also. Okay, so let's start from the beginning with what is entropy of a probability distribution. So I'll give the mathematical definition. Let me start with, it's a little bit easier to start with a discrete random variable, okay? And so we'll start with x is a discrete random variable. I haven't done this before. Anytime you see with RV, that's just random variable abbreviation. Okay, so we started with discrete random variable. The continuous case also works just as well. It's a little quirky, but we'll get to that in a second. The entropy is typically denoted with an H. It actually is named after the principle in physics of entropy, that's where the letter H comes from, is that's where what people use in physics also, or Boltzmann used H. So it's going to be just a number we get that's a property of this random variable. So again, remember, random variables are kind of this mathematical abstraction of that describe a random behavior, a random kind of number, if you will. So it's really, this is a whole distribution kind of thing. This is giving us a property that random variables distribution is what the entropy is going to tell us. Okay. And just the definition is the expected value of a function of the random variable, and that function of the random variable is the negative log of that random variable's probability function. So again, this is the discrete x, so the probability function is a function of, kind of just the discrete outcomes of x, right? So let's see, if I say, but writing this out in the discrete case again, I know this is going to, the expectation is going to be a sum, right? And I'm just going to write this sum is over, I'll just say little x. Little x is going to just be an index over all possible outcomes that capital X can take. Okay, so that little x are the actual numbers, the actual values that big X is going to kind of be able to take on. Okay, and so to do expectation, I just sum over this function times the probability of the outcomes, right? So the probability of the outcomes are p of x. Actually, let me put an xi just to be, so we might sum over I or whatever, but I'll put an x sub I to kind of make it a little more obvious. I'm summing over a bunch of discrete things here. So I take the probability of each of these outcomes x sub I, and I multiply it by the thing I want to take the expectation of. So I'll put the minus sign over there, and I'm just going to multiply this by log of the probability function of xi. Okay? Everybody happy with that? And again, remember in the discrete case, P of xi is an actual probability. When we get to continuous, it'll be the density function, and it won't be a probability of the density, but here, it's the actual probability of this outcome. So because I'm doing x, it's kind of weird, we don't usually put the probability function inside the expectation. We take the entropy is defined so that I do P of xi, I do take the expectation of the log of actual probability function. Okay? And that is the definition of entropy. And so it may not be at all clear why that is a useful definition right now. And let me give now just maybe the intuition for what it is entropy tells us about a probability distribution. So entropy, if I explain it in terms of just intuitively about a probability distribution, is essentially how spread out the distribution is. So high entropy means the distribution is as spread out amongst the outcomes as much as it possibly could be if you get higher and higher entropy. If I get lower and lower entropy, it means that the probability is concentrated to as few outcomes as you can get. So lower entropy, I'm concentrating probability, and higher entropy means I'm spreading entropy out. And that's, in a nutshell, we'll kind of dig into a little bit further here in a minute to get a little bit better understanding, but in a nutshell, that's what entropy is telling us.
So how is it related to variance?
Yeah, so that's a good question. So we'll see in a minute if you're, it's often the case that you, as you increase variance, yeah, you increase entropy. Yeah. So there is a relationship, but another thing is that this is right now we're not. One point to make clear, this is going to be important, and when we talk about maximum entropy principle, is that we're not constraining ourselves to thinking of this is only a Bernoulli distribution, or this is only a geometric distribution, or a specific class of distributions. We might say, I want to look over basically a much broader set of distributions and find the ones that have maximum entropy. So I might have a fixed variance. We'll see in the continuous case in just a second. If I fix the variance, I could actually look over all possible continuous distributions with the same variance and say which one has the maximum entropy within that class. So even keeping variance fixed, I can still fluctuate entropy. It's still possible to change the entropy. So it's definitely related, and it tends to be the case that if you take a distribution and increase its variance, you will increase the entropy, but it's not exactly the same concept, if that makes sense.
So it's correlated with other things too.
Yeah, exactly. So variance is related, but you can keep the variance fixed and actually change entropy. It's possible to do that. Again, if you're saying I'm not going to just restrict myself to a single functional form for my probability function here. Okay. So let's take a look really quickly at let's see. Yeah, so let's think about what exactly is going on here. So if I maybe we'll start with x is a Bernoulli random variable with again parameter theta, let's say. Then we know that the entropy of x, I have two outcomes, 0 and 1, and really, I'm going to sum this up over the probability of 1 and the probability of 0, right? And so the entropy of x is just going to be minus theta log theta minus minus 1 minus theta log 1 minus theta inside the log. Okay? And it turns out if you look at the entropy function here as a function of theta, what you'll see is that it looks, theta goes between 0 and 1, and if I plot the entropy as a function of just how I change theta, then the entropy is going to have a shape that looks like this. Okay? And the peak of this function is at 0.5. And it kind of is minimal at 0 and 1. Okay? And this is kind of the simplest example of interpreting, what does it mean to be as spread out as possible. This is kind of our simplest possible discrete random variable. And what this means is that at 0.5, as you would imagine, then your probability function is looks like this, right? Where this is probability 0.5. And then if I'm at the endpoints here, I've got probability 1 at 0 and probability 0 at 1, or I've got, I'm getting kind of sloppy with my drawings here. I've got a probability 1 at 1 and probability 0 at 0. These are the kind of extremes where I have minimal entropy because my distribution is as concentrated as I can get it. It's either all at 0 or all at 1. Maximal entropy is as spread out as possible. It's at 0.5 equally. Okay, and as you can imagine, anywhere in between the extremes, there's some amount of concentration there. Okay, so this makes sense. This entropy of a Bernoulli makes sense. Okay. Another thing I want to point out here is that the value negative log p of x is sometimes called the information content of the random variable. So, right, it's I of x is equal to minus log of p of x. And I should mention the log here. I've been kind of not putting a base on the log, but you can choose whatever base you want. The concept is still the same. It just kind of is a scale factor in the end of the entropy. But if you want to maximize entropy, it doesn't matter what base you do things in. If you're a computer scientist, feel free to use base 2. And then this will be in units of bits, the entropy will be. If you are a physicist or a mathematician, feel free to use the natural logarithm. And then we say that the entropy is in units of nats, which is natural logs. And I guess if you're, I don't know if you use base 10, but base 10 is you're free to use base 10 also. Anyway, whatever base you prefer. Okay. So, but for the time being, let's actually, let's take a computer scientist point of view and do a log base 2 for the time being. So what is this information telling me? If we think about, let's step back and think about uniform distribution on n different possible outcomes. Okay, so here I've got that p of xi is just equal to 1 over n. So I've got outcomes are x1 through xn. Okay, I'm going to say they're equally likely. So there's 1 over n probability for each xi. Okay. Then this this minus log p of x, what is it telling us? For one of these possible outcomes, the information content of one of the outcomes, and we'll see that what you're basically doing here is, let me back up. If I'm calling this the expected value of the information content of a random variable, what does that mean? It means I'm taking the average information content in that random variable, okay? And so what is the information content in one of these outcomes? It is minus log, let's say, base 2, 1 over n, right? Which is just log base 2 of n, okay? And if I have n possible, let's say, characters that I can produce here, what is log 2 base n, log base 2 n telling me in terms of, let's say, computer representations of things here? Yeah, someone said it.
Number of bits to store?
Yeah, exactly. This is the number of bits it's going to take me to store all these unique, if I wanted to store, and of course I'd have to take a ceiling of this if it's not if n is enough power 2, obviously. But how many bits do I need to store all these different possible outcomes if the outcomes are, we're throwing a twist in it, there's a probability of each outcome. If the outcomes are equally likely, then the number of bits I would need to store all those different possible outcomes is going to be the information content of those outcomes. Okay? And in this case, the average information content is going to be the same as just one of them, and so that tells me that for a uniform random variable of n different outcomes, the average amount of information is the number of bits needed to store any of those things. Okay, so that is kind of this. This gets us into. We're not going to talk about this really beyond this intro to entropy, but this is all part of this field called information theory. Okay, and this guy Claude Shannon, who invented this theory, basically was working at AT&T. He basically was working on communications. So he was trying to send bits across, signals across channels, right? And he wanted to know, and this comes into compression theory, right? How do I most efficiently send messages across a channel where I have limited bandwidth? Okay, and this simple example of the number of bits it takes if I don't know anything about my frequency of characters. Let's call these characters now, because that's what we typically in computer science again, or we have ASCII characters or whatever you will have that you want to send like a message in some kind of language across a channel. Then, if you don't know anything about the frequency of these characters, then you can't compress things. You really need n bits, log n bits to send any of these n characters. Okay? But what Shannon realized was with this definition of entropy, he came up with this theorem that said that you can actually compress a signal down to the entropy of, if you again think of the characters you're sending in this signal as random variables, as coming from a random variable, and that they're independent. So you can expand this when, of course, letters are correlated, the order they come in. But let's just assume they're independent for the time being. Assuming independent characters, you can always compress, I should say, with high probability, you can compress a signal down to just using the entropy of that character set number of bits. Okay, so the average number of bits you can get below log n if this is not a uniform distribution. Which of course, if we think about, let's stick to English for the time being, if we think about the English language, the character z doesn't show up very frequently. The character x doesn't show up very frequently. And so this is not a uniform distribution. This uniform distribution gives us the maximal, just like kind of uniform on Bernoulli gives us the maximal entropy here, uniform on n characters also is the maximum amount of entropy. So anything you do where you have information that there's concentration of probability or frequency in characters, so the S's and the T's and the E's of the alphabet have much higher concentration, and the Z's and the X's and Q's and whatever have lower concentration. Because there is some information there about those frequencies, your overall entropy of characters in the English language is lower than log whatever 250. Well, I guess if we want to just the characters of the alphabet, log 26, if you will, log 2 of 26. So you can get away with much lower entropy, or sorry, much lower number of bits. And the second part of Shannon's theorem actually said, with very high probability, if you try to compress your signal below the entropy of your character set, you will lose information. Okay, so the entropy is very much the theoretical lower bound for how much compression you can do with what we call lossless compression, right? Lossless meaning you don't lose any information. Okay, now implementation where you actually implement these things on a computer, an algorithm that needs to be guaranteed lossless, will probably not achieve the kind of entropy bound. But we do know that you can't go below that entropy bound without losing information. So you can kind of get a sense for how good a compression algorithm is by how close it gets to an entropy bound. Okay, so anyway, this is kind of the computer science-y kind of rationale for this idea of entropy. Any questions at this point? Yeah, so it sounds like most people haven't come across these before. If you, we're not going to, again, dwell on some of this stuff in the history and the information theory and the kind of all these other parts about it, but if you're interested, I would recommend looking up entropy on Wikipedia and elsewhere and reading more about it. It is really kind of important. Really, if you think about all the laptops and phones you have right now with you, we wouldn't have any of the communications and wireless and internet, everything that we have today if it weren't for Shannon and his entropy and information theory. It's really pervasive in all of the kind of communications that we do electronically today. There's nothing that doesn't use it. So anyway, I recommend, we're not going to, obviously, you can take a whole class in information theory. We're not going to dwell on it for too long, just kind of this lecture. Okay, any questions? All right, so yeah, so what does this have to do with probability in Bayesian analysis that we've been talking about? So one definition of non-informative priors is the following. It is if you want to do a prior distribution from some class of distributions, you should always choose the distribution that has maximal entropy. Okay, so, and the, again, philosophy is that you should be non-committal as possible, and so you shouldn't concentrate probability in your prior to one outcome or the other. It should be kind of as spread out among all the outcomes or of your parameter. In this case, of your parameter that you're going to do Bayesian analysis on in the prior, it should be as spread out as possible. Okay. Now, if we're just talking about a discrete distribution like so, we don't get, and all you say is I've got a discrete distribution within possible outcomes, you don't get very many interesting possibilities for what you can do for maximum entropy. It's just uniform with probability 1 over n is maximum entropy, and you're done. So it's going to get much more interesting because when we talk about continuous things, we'll see examples there where it is actually more interesting. But this is the principle of maximum entropy that we're going to use to build non-informative products. Okay? Right. So, okay. So let's take a look at next, how do we maximize entropy? So, yeah, like I said, if I just give you that you've got some discrete distribution with n outcomes, then maximum entropy, I actually haven't proven to you yet, by the way, that maximum entropy is uniform, but you're going to take my word for that for the time being, but we're going to prove it in just a second. So that's not very interesting. So where does this get interesting? This gets interesting when I do want some information. I know some information about my random variable, but other than that information, I want to be maximum entropy. Okay, so I'm going to have some constraints that I add. If you think about it, I'm already adding constraints. If I say it's discrete with n possible outcomes, that's a constraint that there's only n kind of outcomes. Okay. And you can imagine there might be other constraints. Like I might say, well, the outcomes are 1 through n, and I know that this distribution should have mean at n over 2, or something to that effect. Okay, so you might add that constraint that the mean of this should be an n over 2. Okay, and so when you start adding constraints like that, you get some interesting possibilities for the maximum entropy distributions. Okay, so let's, let's do, I'm trying to think if we should do an example or, if I should introduce, I think I need to introduce the continuous case first. Let me just really quickly bring up the continuous case and just mention there is a little bit of a quirk in it that's a little strange. So when you get to continuous, so if x is continuous, then we have something called differential entropy. And let me just write down, if we think of this as, again, an expected value of minus log p of x, now p of x is going to be replaced with little p of x, which is the PDF. And we would get something like an integral, and let's just say this is on the real line from minus infinity to infinity, just for argument's sake for the time being. And I'm going to do the PDF p of x times minus, again, log p of x dx. Now, it turns out for some technical reasons here, this is not ideal because if you do a change of variables here, you change the entropy, which is not something you want to do. So it's not invariant to reparameterization of the real line as a problem. And so what you'll see is people will take this divided by, and this is in the James article you probably saw if you read that, hopefully, that you divide by another measure, m of x. And you can think of m of x as just a base measure that I divide by. So now if I reparameterize the real line, I'm also reparameterizing the measure m of x, and this becomes invariant to reparameterizations. So long story short, there's this little quirk that you have to technically have differential entropy differential to some base measure. But for our purposes, we can kind of ignore that to some extent and really think of this as really being defined this way, and there's some base measure in there that it's relative to, but we don't think about it. In terms of deriving the maximum entropy principle, it's an equivalent derivation, whether that is in there or not. Okay, so now we have discrete and continuous entropy. Let's talk about maximizing entropy. So the idea here is switching back to discrete. In the discrete case, I want to maximize h of x. Okay, and what am I maximizing over? I'm maximizing over just any probability distribution, let's say on, for the time being, on n outcomes. Okay, so I've got n outcomes, and so now I've got any probability distribution of n outcomes. That means I've got, basically, I have any n set of numbers between 0 and 1 that add up to 1, or my choice of possible probabilities. And so I'm basically maximizing over the piece of I. So I'm going to call piece of I just means the probability of an outcome, just for shorthand. Okay, so I've got really a set of of n values, piece of I. I'm going to maximize over those values. I've already got one constraint. I've got one constraint that piece of I is greater than or equal to 0, or I should say two constraints, and the sum of piece of i's have to add up to 1, right? So I've got two constraints already. And now, so let's say, subject to these two constraints, I'm actually going to have the option of throwing in some more constraints if I want to. Okay, so I can add in more constraints about the expected value of this random variable, or functions of this random variable. And these are optional constraints. I can leave these out completely, or I can put them in. It just is whatever you want to do. So I might have some functions, f sub j, of my random variable, and I want to set the expectation of these kind of random, of these values to some value. Let's call it c sub j. Okay? And this is for j equals 1 to whatever. Let's say capital J. So I can throw in as many constraints as you want. So for instance, if f is just the identity, I can talk about what is the mean of this random variable and kind of fix its value, kind of pin that down and say, of all random variables that have this mean, what's the one with maximal entropy? Okay? Or I can pin down and say, I want the mean and the variance to be these values, but given those two constraints, give me the maximal maximal entropy random variable that you can. Okay? Okay, so this is now an optimization problem in kind of n dimensions here, right? Where your n dimensions are kind of in the box, 0 to 1 box here, but I can move around in that box, really in a slice of that box, and because of these constraints, I already know these constraints put me in a hyperplane in that box, and so how do I optimize this? Again, we're going to use like when we talk about maximum likelihood, we're going to just take derivatives of this h of x with respect to the p's and set those derivatives equal to 0, and that's going to be our usual calculus trick to get the maximum. Okay? But Now, unlike maximum likelihood, when we did that, we got constraints, and that's adding an extra twist to the story. So you can't just take the derivative of h of x, because that ignores that you have these constraints that you have to satisfy. Okay, so who remembers from calculus, what do you do when you have a constraint in an optimization problem? Does anybody know? It's named after a famous mathematician. Yeah.
Lagrange?
Yes, exactly. So the Grunge multipliers are how we handle constraints. So when you want to maximize something with constraints, you can convert that from a max subject to just a max where you adjust this function. This isn't obvious, by the way. That h of x is a function piecewise from my notation here. But if I plug that in, we'll see. But you maximize this function plus Lagrange multipliers times your constraint values, if you remember that. So what does that look like? So instead of directly saying max over pi of, and again, let me write it out in terms of pi, so it's so this is the unconstrained problem. What we do with Grunge multipliers is we now add some constant lambda, let's say, times your constraints. And I've got more than one constraint, so I'm going to have to do lambda 0 times the 0. We'll call this the zeroth constraint, this summing to one thing. And then I'll call this lambda 1 through j for these constraints. Okay, so we'll start with lambda 0 and say, and the way you write it is you just set this, basically rearrange this so it's something equal to 0, and you put that in there. So if I rearrange that, it would be the sum of the piecewise minus 1 is equal to 0, and that's the function I put in my constraint there. Okay? Now the lambda zeros, these are constants, and the other lambdas I get. These lambdas are going to be constants that I have to solve for to be able to find the maximum in the end. Okay? But when you set up the problem, you set up the function you had, and then the constraints times these constants, and then you worry about the constants after you solve the maximization problem. Okay? So then I'm going to add in all my other constraints. These are my j constraints I've got here. So j goes from 1 to capital J of lambda sub j times this expected value, and I write the expected value out. It's also a sum over I of fj of xi times pi. Okay, that's the expected value of the constraint. Oh wait, sorry, I need equal to cj. So I need to subtract cj. So that equals 0. Okay, so that's Lagrange multipliers. So that's how you maximize a function that has constraints. You get rid of the constraints and convert them into these Lagrange multipliers. Who's seen Lagrange multipliers before? Is this the first time for some people? Okay, so a lot of people have, but some of you haven't. Okay. Yeah. Without if you haven't seen it before, it might not be obvious why this is what we're doing. But take my word for it that if you want to maximize the function of constraints, you should use Lagrange multipliers. And again, I'd recommend looking it up if you haven't seen it before. Let me just draw a quick picture for those of you that haven't seen Lagrange multipliers, and for those of you that have, this might refresh your memory as to what this looks like. So if I'm in in our case, we're in n dimensions. If I'm in some dimensional space, and I look at the level sets of the function I'm trying to optimize. Okay, let's say these are level sets going up, like a topology or topographic map, right, of a mountain or something, where this is the peak of my function here in this center, and these are kind of the elevation lines as you go down the hill, right? So the gradient, of course, is pointing perpendicular to these level sets, right? So if I wanted to maximize this function, I would go until I get a zero gradient at the peak, right? And that would be the unconstrained thing to do, is if I just wanted to optimize this function unconstrained, I would find the gradient equals 0, and that would be my answer. But now let's say instead I've got and this is always with continuous or usually smooth functions, I should say, differentiable functions, so that we get nice and smooth level sets and constraints and so forth. Let's say instead of an unconstrained problem, I've got some constraint surface like so. Okay, so whenever I have an equality constraint, like I have here, like such and such a function of my thing equals something, that's an equality constraint, that's going to put me on a lower dimensional hypersurface, if you will, that I have to be constrained to. So anytime you say something is equal to something, you lose a dimension. Typically, you lose a dimension in the space that you're working in. So for instance, if I say y equals x, right, I go from two-dimensional xy space to the line y equals x, I lose the dimension. So anytime you have inequalities, you lose the dimension. And so you can think of these constraints as hypersurfaces one dimension lower in your space. Now, of course, we've got multiple constraints, and so it's going to be intersections of lots of these surfaces, but let's just focus on one for the time being. Now, what does Lagrange multipliers do? Lagrange multipliers basically say, if I'm going to stick to this, what I need to have happen is I need the gradient of my original function to be basically lined up with the normal to my constraint. And so what the Lagrange multiplier says, and now I don't know the magnitude necessarily of this gradient. If the normal to my constraint is, let's say, magnitude 1 vector, that's where the lambda comes in, is that it's going to be some scaled version of the normal, and it might be positive or negative to my constraint. Okay, so when I say set my constraint as something equals 0, if I take the derivative of that constraint, I get the normal to that constraint. It's like the gradient to that constraint. And I want that to basically counterbalance this. And so now the derivative of this plus some scale factor times the derivative of this should balance out to 0, is what the Grunge multiplier says. Okay? So that is the principle we're working with. That's a 3-minute introduction to the Grunge multipliers that I wasn't planning to do, but so that doesn't explain all the nitty-gritty details, but just so that you get the, if you haven't seen it before, the intuition for why we use this crazy formula. That's why. Okay? Yeah, and if you haven't seen it before, again, Google that also. so look that up. Read the Wikipedia page for the Grunge multipliers and get a little more kind of feeling for why that works that way. Okay, but yeah, so long story short, if we do the Grunge multipliers, we get our original objective function, which is the entropy that we want to maximize, plus these Lagrange multipliers times the constraint equations that we want to satisfy. Okay? And now what we do is we have an unconstrained optimization problem, and we do our standard calculus trick where I say take the derivative of this with respect to each of the piece of i's, and then set all those derivatives equal to 0. So I really have n variables that I'm taking n derivatives. I'm really getting a gradient, n-dimensional gradient, and I'm saying that all of those, each component to 0. So I'm going to have n different equations that I have to really satisfying. Yeah, question?
Is this one constraint, right? Pi is greater than equals to 0?
Well, there's really two, I mean, and then these.
Pi is greater than equals to 0.
Oh, yeah, great. Yeah, so, okay, yeah, so yeah, you're right, I'm ignoring this, yeah. And the reason I'm ignoring this is, let's see, I'm technically not ignoring it, let's say. We're going to see that, yes, this has to be true, but that's going to fall out of it here at the end. So yeah, so if you think of the P space as, you know, Rn, right, then that first constraint is basically saying stick to the, you know, positive quadrant of Euclidean space. And then this constraint is basically taking, I think it's easier, maybe more if I do 3 dimensions here, is basically saying the sum of all my coordinates has to be 1, and that gives me like this simplex here. So I get like this plane that's in the positive, I guess, octant, if you will, of Rn. So in that case, I get a little triangle, and you think about if I go to n dimensions, I get an n minus 1 dimensional simplex is your probability space, is the space of all possible distributions of n outcomes, is a simplex that kind of looks like this, except imagine higher dimensions, which I can't draw, of course. In fact, yeah, this simplex idea of a probability space will come up again. We'll be putting distributions on these kinds of simplexes when we talk about Dirichlet and Dirichlet processes and things like that later on this semester. So that this kind of concept. So if you haven't thought of like the space of all discrete probability functions before, kind of just do some thought experiments about that. It'll come up again. We'll cover it again. But anyway, yeah, my point is. Yeah, the being positive part, it'll come out of the optimum we get will turn out to be positive. Yeah. Okay. Yeah, and notice this isn't really an equality constraint, so it's really you're still kind of moving around that space freely, and you won't end up going past the boundary into negative territories. Okay, any questions about kind of the general strategy here with the Grunge multipliers and this, that, and the other? Okay. Right, so that's our goal now, is to maximize this. Okay, so this is right, is a little bit tricky, not too bad, but notice that I can basically just really take one piece of I at a time. The piece of I's don't interact with each other. So it's not like P1 and P2 are kind of multiplied together or anything like that. So I really, because it's always inside the sum is just one of the p's at a time. So I can really just kind of think of these things independently, each piece of I, and just worry about one of them. And so if I take the derivative of this guy with respect to Pi, let me call this something so that let's call this my energy of P sub I, or that looks like it's supposed to value. Let's just call this f of P sub I, curly f of P sub I. So if I take the derivative of this f of P sub I, what do I get? So here I'm going to, the sum kind of goes away, and this is really P1 through Pn, I should really, to be precise, but I'll just do it in terms of one of the P sub i's. This, I do a multiplication rule, and I get minus log P sub I minus P sub I. Notice derivative of log P sub I is 1 over P sub I, so I get a P sub I over P sub I. So I get minus 1 there, and that's the derivative of P log P is minus, or sorry, log P plus 1, and is minus 9. the derivative of this is just 1, so that's an easy one. So I just get here, I get plus lambda 0. And then the derivative of this, again, is also really easy because it's just a p by itself, and not by itself, but we just multiply by something here that's not a function of p sub I. So here I just get plus lambda, sorry, the whole sum of j is still there, of lambda j times fj xi p sub I. Sorry, say it again?
P sub I.
You don't have.
Oh, yeah, sorry, you're right. Yeah, p sub I went away. Thanks. All right, somebody's paying attention. Good. All right, so yeah, so that's the derivative with respect to p sub I. Okay, and like I said, there's really this is a gradient. There's n of these partial derivatives, and for each p sub I, and I need all of them to be set equal to 0. So this holds for all of the i's. I'm going to set all of these equal to 0. Okay, and notice that there's really only one p sub I here, so solving for p sub I is really easy, right? So I'm just going to bring this log over to the other side here, and then exponentiate the whole thing. Yeah, if you hadn't called my p sub I, I would have really stuck at this point. But it's good because there's only one p sub I here. I move it over here by adding log pi on both sides, and I exponentiate both sides, and I get in the end that the way to solve this max entropy problem is to set p sub I equal to exponential, now I guess I'm doing a base e log. This could be 2 to the power, whatever kind of thing it does not matter. Of, let's see, I want to make the signs, yeah, minus 1 plus lambda 0 plus sum over j of lambda j fj of xi. Okay, and that is the general form for any distribution that is discrete distribution that is max entropy. It has to look like this. Okay. Now notice, if I have no constraints added here, okay, what happens? I get this whole term goes away because I don't have any of these constraints. And this is just e to the constant in x, right? And notice lambda 0 is just some free parameter that I have to now solve for so that my constraint here works out, okay? And so you basically would just choose lambda 0 so that you get 1 over n. So with p sub I, so let's say there's no constraints, then p sub I is just equal to exponent of 1 minus 1 plus lambda 0. This has to be true for all p sub i's, and this is just a constant. The only constant that we add after 1 is if this constant is 1 over n. Right? So that shows us that max entropy with no constraints other than it's a probability distribution is uniform. And that again, intuitively makes sense that you can't get more spread out than 1 over n. Yeah.
What if you have an infinite space?
Yes, if you have an infinite space, so if n is infinity, so let's say all integers, you've got like, or all positive integers, whatever you want, then there is no max entropy distribution that is a proper distribution, meaning that where the probability is smaller than 1. And so when you have an infinite space and you don't have any constraints, you can't do it. You can't get a maximum entropy distribution. I mean, you can keep increasing the entropy. Basically, if you think about it, I could concentrate the probability all at one number and then just start spreading it out and keep spreading it out, spreading it out. The entropy keeps going up and up and up, but you'll never stop that spreading out process until you've banished everything to 0 and it doesn't work. You keep increasing entropy, but you eventually get something that's not a probability anymore. What we're going to see is that is actually sometimes okay as a prior. I'm kind of giving away a punchline from next lecture on Tuesday, but you can actually have priors that are not valid probability distributions. So, for instance, exactly this that you have kind of led us to, this infinite uniform distribution on the set of all integers, for instance, is a valid prior if, when you combine it with a likelihood, you get a honest-to-goodness posterior probability distribution. So it's actually okay, it's uncomfortable, but okay to have priors that are not really probabilities because they don't sum to 1 or integrate to 1. As long as the posterior is a true probability distribution in the end, because that's the thing you care about.
So there's a prior in some sense in that it doesn't need to be a probability, but just a weighting.
Yeah, exactly. You can think of it as a weighting, exactly, yeah. Yeah, so uniform, we'll see on Tuesday some cases where uniform, but not a real, like uniform of the whole real line, for instance, is a fine prior if it leads you to posteriors that are valid PDFs. There's actually a flip side of that, because you can actually start with a valid prior distribution, that's a probability distribution, and combine it with a valid probability distribution, which is a likelihood, and the combined posterior doesn't integrate to 1. It's infinite. And so you can actually go the other direction and get invalid posteriors, and you can't use those as priors. So you have to be careful. One thing we'll talk about is you have to always be careful that your resulting posterior is something that sums to 1 or integrates to 1 and your discrete or continuous. So you do have to always check to make sure it is. But it's interesting, you can actually start with something like this in the infinite case and get a perfectly fine analysis at the end of your posterior is negative. Yeah, good question. So this is the first thing we get is this really doesn't matter, it's just some constant in there, and if you want to make it satisfy the only constraint you have, which is that everything sums to 1, you're left with the uniform distribution in elements. Okay? Now let's go a little bit further and say, what if I have n elements and I want the expected value to be equal to some, or the expected value of x to be equal to some value. Okay? I'm trying to remember. Sorry, I'm losing my train of thought here for just a second.
That's our only constraint. We have 1j. And
Yeah.
j is equal to x.
Yeah, you'll have something that looks like. So the first thing I want to point out is that this is really just always the normalizing constant, right? Because this is constant in x, and so this term, because you can break the exponent out, this thing's always going to look like exponent of the sum of your lambda j's, fj's of xi. Okay, and this thing really is constant in x, and so you can always just say that, okay, I got to set lambda to whatever makes my thing integrate to 1, so, or sum to 1, I should say. So this is really just, that term's just a normalizing constant. The lambda here just becomes a normalizing constant. And so yeah, so this is really the form of this thing that we really want. And yeah, so let me go over here. yeah, so if I have just one constraint, which is the expected value of x is equal to some value, then what I get is, so one constraint that the expected value of x is equal to some constant c1. The constant doesn't matter in terms of the form of the PDF that we get, PMF that we get. What I'll get is that PI is going to always look like 1 over some constant times the exponential of lambda xi, where I've just got one lambda now, and I have to figure out what the constant is and what lambda is. I'd have to solve for those to get this thing to come out to the expected value the way I want it. And the same thing is going to hold if and really I need this to be, when you look at continuous, I don't have time to go through, let me just say, for continuous, if you do this maximization problem, I was going to go over this a little more carefully, but I think I'll just leave it a little bit vague. If you do this maximization problem for continuous, you're now optimizing over, let me write it down a little bit more carefully. Your h of x, like we said, is this differential entropy, which is that integral over there on the far board, integral of p log p. Now what am I optimizing over? I want to maximize over all possible p's, where p is a density function. So I'm maximizing entropy over a space of functions. Okay. Now, I'm going, so long story short, there's a whole area of mathematics called calculus of variations, which basically takes you from maximizing over a set of finite values, in that case the p sub i's, to maximizing over spaces of functions, which is really an infinite dimensional variable. So this is a function. If you imagine I've got infinite degrees of freedom in how I can change this function, I'm maximizing over this function space, but you don't have to know all of this, the calculus of variations, but the long story short is the derivation looks very similar. It looks almost identical, and you just replace sums with integrals. And what you get is that the function that solves this with the same types of constraints is something, as you imagine, it's a PDF of the form 1 over c times the exponential of the sum of these lambda j's times these constraint functions, like so. Okay, so it's of the same form. The only difference now is that your constraints are continuous functions or the differential functions typically, and this is obviously a PDF now instead of a discrete. It's a continuous thing. And so the same principle here. This one makes a little more sense to us. This thing makes a little more sense to us in the continuous case because this guy looks like when you constrain just the mean, you end up, and I'll just throw in a negative sign because we usually typically have lambda being a positive number, but to make this come out to be a probability, you have to have a negative times a positive number there, and you get the exponential distribution. Okay? Now, of course, this is only from 0 to infinity, we know the exponential distribution. Similar to the point about the uniform spreading out over the whole set of infinite values, if I were to try to do this from minus infinity to positive infinity, and say I fix the mean, you also don't get a valid probability distribution. So you can't get a maximal entropy if you're on the whole real line and say I want to fix the mean. Okay, so there is no such thing. Now, this is where I wanted to get to, and I'm kind of rushing through a few things, but the last one example I'll do is what if we have not just the mean fixed, but let's say we have the variance fixed, and I'll just say once you set the mean, you can just, instead of variance, just specify what is the expected value of x squared, of course. And so what if I fix both of these things? So I fix the mean and I fix the variance, then I know that that's going to lead me to, based on this same form of this, it's going to lead me to something, some constant times exponential of minus lambda 1. Doesn't matter. Minus here. It's going to lead me to something like that. And given Tuesday's discussion, what can we say about a PDF that's in this form?
That's in the exponential family.
It's exponential family, but it's even more specifically, what exponential family? Yeah, Gaussian. So remember what we said on Tuesday, anything that looks like exponential of a quadratic is going to be a Gaussian. Now, we know that the sign of lambda 2 is going to have to be negative and so forth and so on, and we get that whole ABC and complete the square thing to bring in whatever we need from the normalizing constant. And you can rearrange this guy as the point to look like your standard Gaussian PDF. So the bottom line here is that this kind of max entropy form tells us that if I do specify the mean and the variance of a real value distribution on the whole real line, then the Gaussian is the maximum entropy distribution. Yeah, question?
So, considering the case where you fix just the mean, would you then, like the exponential distribution goes from 0 to infinity, would you then need to say where you want to move that distribution and which direction you want, whether you want to go from 0 to negative or c to infinity or c to negative infinity?
So this guy up here, and I didn't do the minus sign there to make it look more familiar to us. This guy here does work as a distribution from 0 to infinity. It actually works from any fixed point to infinity. And actually, if you did from some fixed point to negative infinity, I would get rid of the negative sign, and it would work also. It's just kind of a reflected exponential distribution. But you could also shift where that 0, it's just 0, you can shift it to some other point. But you can't go from minus infinity to infinity, because then you're guaranteed to get the part of the exponential that flies off to infinity and can't integrate. But if I chop it off, then I can always, integrate the stuff to one side. And I can flip it if I need to go positive or negative. So you could do this only on a half of a real line. You can't do it on the full real line.
Yeah, but wouldn't you also be forced to make the decision on which half and where you move it?
No, if you make the decision which half you want first, that's fine. Because you can change what if lambda is positive or negative, and that changes which side it will go to. So because you have the option to change lambda at the end of the day. You can do it from any kind of half line you want. Yeah. Okay, so I think that's all the time we have. There's a couple other examples of max entropy I wanted to get to, but we'll save those to